Welcome, everyone. My name is Abba, and I will be your moderator for this session. A quick reminder that we will have time for a brief live Q&A after the presentation. So be sure to use the Ask a Presenter tab to ask questions and engage with your fellow attendees. And now it's time to welcome Xianyang with Tencent to the stage for their session, efficiently managing table with thousands of columns using Iceberg in Tencent. Take it away, Xianyang.
Okay. Okay, thanks, Abba. Thanks, everyone. My name is Xianyang. I'm a senior software engineer at Tencent, and I'm very honored to be here and have a chance to share our experience and the expertise for using Iceberg to manage wide table in Tencent. So here my shared topic is efficiently manage table with thousands of columns using Iceberg in Tencent. So first, let me give you some backgrounds about the wide tables. Here is you're aware from a design perspective, and the wide table are not a really good choice, but from a user perspective, the wide table are very easy to use. Here are two typical scenarios. The first one is the advertising. Due to the business complexity, the advertising business involves information from many dimensions. And some of the information aspects are needed for the target placement. So the white table for advertising is very suitable. The second scenario is for the machine learning or deep learning. Feature engineering concatenates the basic information, the feature data, lab data, and more into a white table. So the white table provides a unified data set, which is easy for the training and evaluation. So my sharing starts from these two points. The first one is the problem, and the second one is the characteristic, or called the requirement about the white tables. The first is the problem. Let's say your white table are often very too large. They are also petabytes for a single table. So with the default configurations, there are tens of the millions of data files and thousands of manifest files. Due to so many data files and manifest files, we got a very poor task planning performance. And also the batch writing need many memory. Writing can easily cause out of memory error. The second thing is about the it can be caused the characteristic or the requirement about the white tables. So the table has so many columns, but a lot of those columns have the same variable. The columns are added and removed frequently. So the column management tool for linear storage is a requirement. A user want to keep the storage small to remove those unused columns. So the first thing we should to do is reduce the file count. Here, let me see the Iceberg file architecture. The top layer here is the Iceberg catalog, which you could choose, such as the RESTful catalog, Hive catalog, or some other choice. And the catalog stores a pointer to a metadata file, and also the Iceberg catalog acts as provides the global lock for the global lock to protect the table operations. The middle layer is the metadata layer. It contains three types of files. The first one is the metadata file. Here, the pointer is pointed to this metadata file. The metadata JSON file contains some basic type of information, such as the table format version, table schema, table partition spec, and the table property, and also some other type of informations. The second one is the manifest list file. Each snapshot here, for example, here the snapshot one point to manifest list file. Each snapshot only point to a single manifest list file, which records a list of manifest file. Each manifest file records a bunch of the data file, and each the item records the data file location, partition, column matrix, and more. The bottom layer is the data files. Data is stored as a data file in the Apache, awk, arrow, or puffin format. So why the column increase could produce so many data files and many data files? The first reason is the few records per file, or the number of column increase, and with the fixed target file size, each file can store few records. So in turn, we need more of file to store those data. The second reason is for the large manifest entries. So there are many and many data files, and also for each data file you could see here, you could see this data file which is stored in the manifest file. It contains 6 fields about the column matrix, and all those column matrix in form of map. So, and also the key of the map is the column ID. So when the column increase in each manifest entry here, consuming more storage resource. So due to the above reasons, we need more data file to store the data, and need more manifest file to store those data file. So why the column with the column increase could influence the task planning? Here is a SQL query which user has submitted to the SQL engine. So it selected from the event table with field condition on the event times event TS here. This table is also partitioned on the event TS. So at the Iceberg perspective, when to the task planning, Iceberg will add an extra partition filter. Here is the event month equal to 1. When to the task planning, Iceberg first will use this partition filter here, event month equal to 1, apply on all the manifest list file to filter out to unmatched manifest file. This step only need to create a single file, so it is much faster. And then for all those remain manifest file, Iceberg will use the user provide filter here. The event TS between some conditions apply on all those manifest file. And here for each data file, it will use the column matrix which we have mentioned before, and then the filter condition to determine whether this data file should read or not. So this step will much slow when there are many remain manifest files. So when the column increased, the metadata increased, and then it could influence the task planning performance. Here are some tips for reduce the data file count. The first thing we could do is increase the target file size by this type property, right pointer target file size bus. And the second one is using the ZSTT instead of the gzip for the older tables. In our production, we noticed that compared with the gzip, the ZSTD could reduce the file size by 30% on average. The ZSTD is also seen as the default compression codec after the 1.4.0 version. So you could change it manually for the older tables, which the default codec is the gzip. The third one is merge the small files into a large one by using the rewrite dead files action or procedure. It is a Spark action which will rewrite all those small files into a large one, and in this way it could reduce the file count as well. The last one we have done is limited the small files count, small file count generation per commit. This is used to avoid user wrong operations. This will be introduced in more details later. So after we have reduced the dead file count, there are still some tips for reduce the metadata file count. The column in the dead file, the column matrix take up the biggest chunk of the storage, and the column matrix are most used for the task planning to skip unmatched files with the filter condition. So we can disable those matrix which those column are never used for filter condition. You could disable it with this table property. With this change, this could reduce the manifest entry size a lot. But there are some column metrics such as value count cannot be disabled. So each manifest entry still be large. The second one is increase the manifest target size with this table property, but to be cautious, you should change it carefully because most of the steps of generation will merge the manifest file. This should be fine to keep the manifest size count small. However, after you change the target manifest file size, the first step generation after that needed to rewrite all existing manifest files to meet the target file size. So this could take much longer when you have many manifest files. So the much careful steps here is the first you should temporarily disable the commit manifest merge enable this type property. This will disable the manifest merge process, and then increase the manifest file size. The third step is you call submit async job called the rewrite manifest file action or procedure to rewrite all those existing manifest file to meet the target manifest file size. Finally, after these rewrite actions, we could re-enable the commit manifest file merge enable tab property to re-enable the merge steps. The last one you could take a try is use the ZSTD for the manifest file compression or manifest list file, both for the compression rate and performance. But this needed some patches. You could find it in the GitHub. We have contributed this, but it is not get merged. And also there are some other people also contributed the similar thing. Now let's see the optimization we have done for the batch data writer with Spark. Here is the Spark batch write. each task of the Spark read the data from a source input, such as the HDFS or some similar, or the object distributed file system or distributed object store, and each task will generate multiple data files or several data files, and those data files where this task result will send back to the Spark driver. The Spark driver will hold all those task results in the memory until the next task finishes. So we have mentioned that the each data file could occupy much larger memory capacity, and also with the data file size increase, this could very easily get out of memory error. This is very often when we batch run terabytes data in one job. And there's still there are another problem that we could get one with the batch run with Spark. But this problem we have already fixed and contributed to the Iceberg community. So this problem shouldn't be happens when you use the latest or some refreshed Iceberg version. The problem is I wanted to expand here is to expand the backgrounds of optimization. The problem here is when the next task finishes and the result is sent back to the smart driver. Smart driver will commit all those data files to Iceberg. The first step it will do is write all those data files to a manifest file, but all those data files are write into a single manifest file, so the manifest file could be very large. We have noticed some in the past. We have noticed some manifest file can be 100 megabytes or much bigger. The solution is when write the data file to manifest file, we will check the manifest file size and roll into a new manifest file when the size has met the target manifest file size. So with this change, we could get a more reasonable size manifest file. So we have changed the commit step. So here the driver will stage receive the data file into a manifest file, and this step is same as we have mentioned in the previous page. When the data file write into the manifest file, we will check the target, check the size, whether have exceeds the target file size. If its size has achieved or larger than the target file size, we will roll into the new manifest file. So and then we will commit those manifest file to Iceberg directly. So with this change, we need a much lower memory for the driver. This solution is more like the filling size solutions. So with this change, the driver memory has decreased from the 64 gigabyte to 8 gigabyte, or much lower. There is another thing that we have done for the Spark batch write. This is to limit the number of small files generated per write. We have there are some people also can do some strange or some mistake when operate the tables. For example, we have noticed that some job could produce very large small files. When we debug it, we found that the user has set the wrong partition spec or some similar things. So we have added a check here before the job finish, before the job committed to the Iceberg. The checker will check the small files generations for each task, for each partition, and for each commit. The default size is very large and could be, and the default limitation size is very large and could be configured by the table property. So it will not influence the normal task route, but it could help us to find out those abnormal or wrong table operations. So now let's look at the remove columns. Here is a table for phone, and here have 5 columns, and this 5 columns are the property for phone. So from the time perspective, the persistence duration of the columns is the same. So when each record here with 5 columns right into the table, it will removed or expand together. So all the column has same persistence durations. However, from the scan matrix, we have tracking the column scan matrix to record each column scan times. From the query times, we can notice that some columns has much lower available. For example, here the headlist only have 2 times query times. So from a table manager, this column has much low available for the advertising on time service. So user could change it with could remove it or replace it with some much useful columns. So after remove the columns, how to remove all those data. So to keep the storage small is a question, and is also a challenge here. So now let's look at what happens when user remove a column. When you submit use this circle here or to table to drop a column here, column 2, apply on the Iceberg. After that, the table could have 2 parts of data. The left side is existing data. Those data have the removed column here. It has 4 columns. While on the right side, this is the new data that write with the new schema here. So it only contains 3 columns here. There are 2 solutions for those existing files. The first one is keep them here, and is by over time. You should call the is by snapshot to remove it. So, but this approach will occupy storage space during the retention period. The second solution is rewrite them with the new schema by calling the rewrite data files action or procedure. Here is what happens. Here is the picture that shows what happens when user call rewrite actions or procedure. So when the rewrite actions execute, the Asperger will print all those data files First, with user-provided conditions. For example, you only want to rewrite data files on given partition or with some given filter condition. So first, it will filter out those data files with a filter condition, and then it will play those files based on the size. Here is first compare each data file size with the target file size. For example, here it select out two data files, data file 1 and data file 2, because their size is smaller than the 512 megabytes. And then those select those filter or select that file will be packed with the type new schema into a new data file. Here it generates new data file 4 with 3 columns, the new schema here. And after that, it will use this new data file to replace those data file 1 and data file 2. And finally commit the new data file and the existing file to the Iceberg. So you should find the problem here. If the file size is larger than 512 megabytes, it will not be selected and it will not be rewrite. So the data files 3 still have 4 columns. The remove columns still adhere to occupy the storage capacity. So we need some way to quickly find all those data files. Our solution is record the schema ID when generate data file. Here, for example, here are 3 files, data file 1 to data file 3. And here is we record the schema ID when generate the data file. And when we want to find out all those data files with older schema, for example, here the address is being removed by the user, so we want to find out all those old data files with the schema ID one. We have extended the task planning to support the file pooling based on schema. So when Spark select when the Iceberg select those data files, we will apply a schema evaluator on all those data files, and the schema evaluator will use the data file schema D and the table metadata where here has a mapping of mapping from the schema ID to table schema. It will use those two information to determine whether this file is an old schema or not. So here we could quickly find out the data file 1 with the old schema. The another problem for the rerun data file is that the rewriting is not a cheap operation. It needs to read those column storage data into Spark memory. It needs to for each column here. It needs to decompress the data and decode the column storage data, and then convert the column storage data to the row-based data, and then Spark will need to deassemble the row-based data into column Y, and then for each column we need to encoding and also compress it. So here we just want to rewrite all those unused column here, but for all those needed data, we have to do some waste computation because we need decompression, decoding, and column to row and row to column compression, and then we need to re-encode it and recompress it. So there is a lot of computing waste, and those encoding, decoding, compression, decompression are not necessary for those needed columns. So first, let me see the Parquet file format. Here is the file architecture for the Parquet file. The Parquet format is the default file format for the Iceberg, and also it's what used in the big data area. The Parquet file data can split in two parts, the data part and the metadata part. The data part is stored at the beginning of the file, and the metadata file is stored at the end of the file. Here the data is consistent of the row group and the column data here has 4 parts. This 3 part is the index data. It contains the column index, offset index, and the bloom filter. Those index data that can be used for data skipping. For example, you could use the filter condition and those column index to skip read those unnecessary columns pages. And the end of the file is the file filter. It stores the basic information for this file, such as the file schema, the file version, and the start position for each row group, and all some similar things. And each row group is composed of the column trunks. Those column trunks store the same order of the columns in the schema. And the each column trunk is stored consecutively with pages. And here is for each page. So it contains 4 parts of data. The first one is the page header. It defines the basic information for this page, such as the compressed size, the encoding method for this 3 parts, so the remaining 3 parts. There is 2 levels called repetition levels and adaptation levels. They are used for reassemble columns data back to row-based data. And the values is encoded and compressed with some codec. The page is small or the smallest story unit for a Parquet file. And with the Parquet file, you could see that there's low relationship between the column trunks. Each column trunk is storage pages by pages, and also there's the data and the metadata stored separately. The data is stored at the beginning of the file, the metadata is stored at the end of the file. And also the encoding for the data is only related to the data type and the file version. So those features allow us to remove column without decoding and decompression. So we could remove the column in column way. So with the Parquet column storage characteristic, we could merge file in a totally column way. The first one we have implemented, we call it merge by Parquet pages. So the first thing we should to do is group all those row groups in the files in a task. And here we these 2 row groups is grouped together, and those row groups in a row the row group size in a group summed up to the target row group size. So here the 2 group size sums up to the default row group target row group size is 128 megabytes. For each group, we merge those row group in column Y. We merge the column trunks by column trunks. We merge these column trunks, then we merge these column trunks, and in each column trunks we merge the two column from the row group 1 and row group 2 by pace. So here for each page, we will read the data from the row group. Here it will contains the repeating level, different level, and the values. And we will check the encoding way, whether the existing page encoding way is same as the new column trunks encoding way. We have said the encoding way is only related to the file version and the data type, but it still could be different for different row group. For example, the row group or the column in this row group, the encoding way is the dictionary encoding, while it has the plain encoding for the column in this row group. So when the encoding way is not the same, we need to decompress and decode the page data back to the row-based data, and then re-encode it with the new encoding methods. And then we need to compress it again. However, for the repeating level and the definition levels, their encoding way are almost the same and only related to the file version. So for this two part of data, we can copy it directly. We don't need to re-encoding them again. If they have the same encoding, then we should check the compression codec. If the compression codec has changed, we need to recompress the whole pages. However, in this way, we just need to recompress the page. We don't need to decode and recode the values. So finally, if both the encoding and the compression codec are the same, we could just copy the data directly, copy the page directly to the target column trunks. After process each of the page, we add a check here to check the row count and the value count. But this solution has some is not applicable. So for columns that have data time evaluation evolution of the inhibited bloom filter, this is because when, for example, when the column in this row group with the integer data type, however, it could be promoted to a long data type in this row group, so we can't merge the page with different data type from the different row group directly. And also the bloom filter is applied on the whole the row group. So we can't merge to bloom filter from different row group from merge those bloom filter from different row group. Here we have done a local benchmark with the TBCTS stored sales tables and the table with 10 million piece of data, and the data is compressed with a STEPy compression codec. We have compared two scenarios. The first one is without the codec change. The second one is change the codec from STEPy to ZSTT. So from this benchmark result, you could see the performance improvements is very visible. Without the compression codec change, the performance improvement get about 10 times performance improvement. Even though the could exchange from SAP to the STD, we still could get a 3.5 times performance improvement. So we have we'll have to process those columns that have data evolution has set the Bloom filter. We call it this way is column reading and column write, and this is because we for example here this column for example has some data promotion or has enabled the Bloom filter. For this column, we could read the data from those two row groups in column Y and then write to the new column trunk directly. We don't need to convert the row column storage data back to row-based data and then convert it back to the column storage, column Y data. So this way we need to decompress and decode the data from the column storage. However, we don't need to convert the column-wise data into row-based data and then back to column data. Thus, avoiding the overhead associated with such conversions. Here we have done similar benchmark with the same data, and it also have two scenarios. The first one is SAP to SAP. The second one is SAP to the CD. You can look here. Still could get some performance improvement. We could get about the performance improvement is about 1.6 to 1.7. However, you know that the stock size is not a white table. It only contains 18 columns. So for a white table, the performance improvement is much bigger. Here is the production results. We could get 10 times performance improvement for only column removes, and also the result could get 3 to 4 times performance improvement. This contains the column remove and also the rewrite small file to merge the small files to large files. And also the result is not only suited for white table. Here is two pictures. The above picture is a white table. You could see here the result performance is under 50. After we have enabled this result new features, the result performance has increased very obvious. And here is a lump table. It only contains about 20 columns, but the table is also very big. It have several terabytes data, and the rewrite performance has improved from under the 500 to about the 1,000. And also we have recorded orange files for easy debug, and each step we have performed the network verification and support fallback. When we meet some problem, we fall back to the original smart rewrite actions. So that's all. Thanks all. That's all my sharing, and thank you for looking into this. If you have any question, you could reach me at the email address here. And finally, I would like to express my gratitude to the community and the selection committee to provide this opportunity, and also thanks for their hard work in select those topics. So that's all. Thank you.
hear me?
Yeah.
Okay. So up next in track 2, we have leveraging Apache Iceberg to build Xiaomi's unified lakehouse platform presented by Yujang Zong. So see you all there. Thank you very much. Bye.
Bye-bye. Thank you.